Now that we've figured out the axioms for the real numbers and determined that there are actually some real numbers that are not rational, we want to start heading towards figuring out how many irrational numbers there are, in some sense. To do that, we're going to first talk a little bit about something called cardinality. We're going to think about two methods of determining when two finite sets have the same number of elements. We're going to extend one of those methods to infinite sets and define what cardinality is. Then we'll demonstrate how the definition is used to prove two sets have the same cardinality. And then finally we'll discuss some, I'm going to call them philosophical conflicts related to the definition of cardinality. You'll see when we get there. So first I want to answer a very simple question and sort of dig into some of the details of how we can answer this question. So we have two sets here, the set containing the letters A, B, C, D, and E, and another set containing the numbers 1, 2, 3, 4, and 5. And the question is, do A and B have the same size? And of course you're laughing at me, the answer is yes, but I want to think about the methods that we would use to show that they have the same size. And I can think of two different but equivalent methods. The first method is we could just count the number of elements in each set, see if those numbers are identical, and if they are, they have the same number of elements. So we count the numbers of elements in A. Each of them has 5 elements. That means they have the same size. There's another method we could use, however. We could take an element from each set, put them in pairs, and see if they match up evenly. So here's what I'm talking about. Take the letters A, B, C, D, and E. We match up A with 1, B with 2, C with 3, D with 4, E with 5, and we notice that they match up perfectly. The advantage of this method is that we don't actually have to figure out how many elements are in each set to determine that they have the same number of elements. We just have to make sure that they match up correctly. So the question may occur, is there only one way of matching up the elements? And of course not, right? If we wanted to put the numbers in a different order, match them up, as long as we match them up in a way that, that matches them up into distinct pairs, that's all we need. And we just need to find one matching. We don't have to find all the ways that we can match. I mean, you can, as just a general mathematic questions, that you can say, how many different ways can we do this? That's fine, you can do that. But if I just want to know whether the two sets are the same size, I just have to find one matching. So, so what do we mean by matching? Well, we're pairing up elements, and if we're thinking of that from a mathematical point of view, that's a function, right? So really, when we pair up the elements of A with elements of B, we're defining a function from A to B. And when we match up elements, well, let's think about it. We can't have two elements in A get matched up with the same element of B. That would mess up the counting. That would undercount what the elements in A and overcount the elements of B. And that means our function has to be 1-to-1, or you might have learned this as injective. We can't leave any elements of B out of this matching. If we did that, then we'd be undercounting the elements of B, overcounting the elements of A. That means F has to be onto, or you may have learned this as surjective. So our conclusion is, if we have two finite sets A and B, we can prove that they have the same number of elements if and only if there exists a function f from A to B that is 1-to-1 and onto, or again, you may have learned the term bijective. Well, what about infinite sets? Well, obviously we can't count the elements in infinite sets. That would take us way too long. But we can use the definition above of using a function that is 1-to-1 and onto between the sets, and if there is such a function, that tells us that they have, in some sense, the same number of elements. So let A and B be sets. We say that A and B have the same cardinality precisely when there exists a function f from A to B that is 1-to-1 and onto, or again, you could say bijective. So let's do an example. So let B be the set of even natural numbers. So that means B is the set of all n in the naturals such that n equals 2k for some k in the naturals. The question you might ask is, do the sets n, the naturals, and B have the same cardinality? Well, let's see. In order to do that, we'd have to find a function from n to b that is 1-to-1 and onto. So I'm going to make a definition. F from n to b f of k equals 2k. So the first thing I want to do is make sure that this function has the correct domain and codomain. Right? Obviously, we can multiply any natural number by 2. That's a fine domain. But are all the outputs going to be in B, in the set of even natural numbers? Well, let's see. So if k is in n, then 2k is in B, right? An even number just means it's a multiple of 2, right? That means that the f has the correct domain and codomain. All we have to do is prove that it's 1 to 1 and onto. So let's prove that it's 1 to 1 first. So we're going to assume that f of k equals f of m, and we want to prove that k equals m. So let's see if we can do that. Well, we're assuming f of k equals m, f of k equals 2k, f of m equals 2m. If we multiply both sides by 1/2, we get k equals m. It's 1 to 1. For the onto, for the surjective, we're going to assume that n is in B, and we're going to find an element in the natural numbers that maps to n. We're going to prove that there is some k in the natural such that f of k equals n. So we know n is in B. N is in B, that means it's an even number. That means we can write it as 2k for some k in the naturals. And then if we take f of k, that gives us 2k, which is equal to n, and that tells us every element of B is an output of the function. That tells us that f is 1 to 1 and onto, and that means that n and B have the same cardinality by definition. So since n is often called the set of counting numbers, this leads to the following definition, right? So we really appreciate being able to count elements, and this tells us we can count elements in other sets as well. So let A be a set. We say that A is countably infinite if A has the same cardinality as n. We can count the elements at n, 1, 2, 3, 4, 5, etc. The corresponding elements of A, when we match them up in a 1 to 1 and onto way, we can count those as well. We say A is countable if it is either finite or countably infinite. We include finite sets as sets that we can count. And we say that A is uncountable if A is infinite but not countable. So here are some examples of countable sets. We'll be looking at this in some of the examples, or actually, if we don't, you can ask me about them in class. I'm glad to talk to you about those as well. Obviously, the set of natural numbers is countable. It's f of k equals k is a great 1 to 1 and onto function between those. The set of even natural numbers, not just the even natural numbers. We just proved that. Turns out the integers are also countable, even though they include some extra numbers. Here's one that's a little bit disturbing. The set of rational numbers is also countable. If you want to see that proof, I'll be glad to show you. That one. Some of those are unsettling, right? So some of those make you feel uncomfortable about being countable because of the way we think of sets having the same number of elements. So one thing that mathematicians often say in a kind of casual way is that cardinality of a set and the size of a set mean the same thing, essentially, conceptually mean the same thing, right? But there are some things that are a little bit unsettling about that, right? We have some sets that have the same cardinality as some of their proper subsets. We looked at the natural numbers and the even natural numbers. Even natural numbers is a proper subset of the natural numbers, and yet they somehow have the same number of elements. That's an uncomfortable idea. We have sets that seem to have wildly different numbers of elements, but somehow have the same cardinality as well. The natural numbers seem to have way fewer numbers than the rational numbers seem to have way more numbers than the natural numbers. It seems weird that they would have the same number of elements. So it is okay for you to be uncomfortable with this idea. It is okay for you to think, well, look, cardinality is a fine concept. Having the same number of elements is also a fine concept. I just don't think they're the same thing. That's okay. To be in this class, you don't have to accept that cardinality is the same thing as the size of a set. And if you really want to make a big deal about it on your homework, you can include the following disclaimer if you like. You can say, submission of this assignment on cardinality in no way implies that I accept cardinality as being a valid measure of the number of elements in an infinite set. fair. But you do have to accept the definition of cardinality itself. You can say two sets have the same cardinality. You don't have to accept that they have the same number of elements. Alright, so now I think you're ready to work on some of the activities for cardinality at the link below this video.